Superposition is always better than double integration. If you can solve a problem with superposition, if your beam matches your tables, you should always do it that way. Double integration is only the backup plan in case you have some scenario that's not in one of your tables. So for this problem, I'm going to prove it to you by solving it both ways, first in superposition in like 2 minutes, and then double integration, which will take longer than 2 minutes. So I'm trying to find the deflection at point A, which is at the end of this cantilever beam. I have a triangular distributed load and a point force. Fortunately, both of these types of loads are in the table, and I can find the deflection at A by just finding the deflection caused by the distributed load and the deflection caused by the point force, and just adding them together. And both of these types of loading are going to have their maximum deflection all the way at the end of the beam. So I can just grab the deflection equation, the Vmax equation. I don't have to use the full elastic curve. So for the point force, this distance A is just the full length of the beam because the point force is all the way at the end. So I'm just plugging in 2.5 anywhere I see L or A, and 50,000 for the force because I'm going to convert everything to newtons and meters, like regular base units, not kilonewtons or gigapascals or any of that stuff. So gigapascals is easy, 200 times 10 to the 9th Pascal, but the conversion from millimeters to the 4th to meters to the 4th for I, the moment of inertia, yeah, I'm going to have to actually write this out. So 1,000 millimeters is 1 meter, and raising that to the 4th power, so it means I'm moving my decimal place over 12 places. So this gets rid of 10 to the 6, is 6 of them. The 129 is another 3, so I'll have 3 zeros in front, 0.000129, and that's in meters to the 4th as the area moment of inertia after doing the unit conversion. And then just plug in all the rest of the numbers also for the triangular distributed load with the 90, again, converting that to 90,000 newtons per meter. And these are both going to be negative numbers, like negative 0.01 and negative 0.0045, because they're both being pushed downwards, which makes sense. So we're essentially adding them together as a magnitude, 0.0146 meters, 14.6 millimeters as the deflection downwards at the end of the beam. Superposition, just like that, like 2 minutes, easy problem, done. Now let's see how double integration compares. It's way worse. Spoiler alert. So double integration method for beam deflection, the thing you are double integrating is the equation for moment. So think shear and moment diagrams. You need to get your moment diagram and the equation for your moment diagram. So this process all starts from the beginning, a free body diagram to solve for reaction forces. So sum of forces in Y, sum of moments about point B, solving for the force at the wall and the moment at the wall. We can then draw our shear and moment diagrams. Shear and moment diagrams have to start and end at A. So my shear diagram starts by going straight down 50. Then because of the triangular load, the slope will start at 0 and keep getting steeper and steeper to the right, and eventually has to get to all the way at the right side of the beam to 162.5 because that's the upward force, is 162.5 to take us back up to 0. We also could have figured this out by the area of that triangle, 1/2 base times height, so 1/2, 2.5 times 90, that would be so 2.5, 1/2 times 2.5 times 90, that would be 112.5, which with the 50 does give us 162.5, confirming that we haven't made any math errors yet. So now the moment diagram, just like shear diagram is the integral of the loading, the moment diagram is the integral of shear. So we're starting at 0 and going to end at 0. So we start at 0. There's going to be a negative slope pointing downwards because shear is negative 50. And it's going to keep getting even more and more downwards because at the other side, the slope will be negative 162. So this will actually be, while the shear diagram was a parabola, the moment diagram is actually going to be a cubic function, but just going pointed downwards, concave down. And we know we're going to hit 218.75 over on the right side of the moment diagram because that's the moment at the wall that we saw from our free body diagram was 218.75. Yeah, you want to come up here? All right, your TA Serenity is a pro at coming up with, your TA Serenity is a pro at integrals, so she wanted to come up and help us out. What we need is a function for this cubic, this moment curve, this green line. So we're going to start off by writing the function for v, and in fact, it might help to do this by just drawing the method of sections for this beam. So we're going to have the 50 on one side and a partial triangle up to, some point where the base is x and the height will be 36x. And why isn't this 90? It's because remember 90 was the very peak after a distance of 2.5. So the slope of that triangle is actually 36, 90 divided by 2.5. So after we've gone over a base of 1, it will be at a height of 36. Over 2 will be up to 72, and then 2.5, it's up at 90. So on my tiny little method of sections drawing, if we summed forces in the y direction, we would have negative 50 pointing down. We'd also have the area of that triangle, 1/2 base times height. So 1/2 x times 36x. Which is negative 18x squared. So v is going to be negative 50 minus 18x squared, which we get by a sum of forces on this method of sections piece of the beam. And we can check if that actually works by plugging in some numbers and seeing if that matches our shear diagram. If we plug in x equals 0, we get negative 50. So that matches the left side. If we plug in x equals 2.5, we've got negative 50 minus 18, 2.5 squared, negative 162.5. So check. Yes, this does seem like it's working. So now for the moment diagram, we could do the same thing, just using sum of moments on the free body diagram method of sections. But actually, because the triangle is going to be, finding the leverage arm for the triangle is not immediate. Just take an integral, right? We're already going to have to do a million integrals anyway. Just going to integral v. So the integral of 50 minus 18x squared is going to give us negative 50x minus 6x cubed. And plus c, when you do an integral, plus c. We can solve for c by plugging in x equals 0. Since we know the left side of our moment diagram is at 0, negative 50, 0 minus 6, 0 cubed plus c has to equal 0. C is 0. And we can check and see if this equation matches by plugging in x equals 2.5, right? So negative 50, 2.5, minus 6, 2.5 cubed gets us to that 218.75. So cool. Now we can finally start the double integration method. So it's obvious already why superposition was better. We were already done with the problem by this point. We did all of this work, shear and moment diagrams, to write an equation for the moment curve just so we can start the double integration method. So the first time we integrate, we're going to be able to solve for angle. This is the angle of the beam. It's weird that you integrate moment to be able to solve for slope. But so we integrate that, we get negative 25x squared minus 1.5x to the fourth plus another c. I'll call it c1. We do the double integral, right? We integrate slope one more time. That will help us find deflection. And of course, we've got these EI terms also on the left-hand side. I'm only ignoring them for now. They will be important later. So we integrate slope to get our equation. So EIV is the integral of slope. So we get negative 8.33x cubed minus 0.3x to the fifth, C1x, and then another constant of integration. I'll call it C2. 2. To solve for these constants of integration, we're going to have to use information that we know about slope and displacement. We know that the slope at the wall has to be 0. A fixed joint resists rotation, so the slope of the wall is 0. So for our slope equation, if we plug in x equals 2.5, that has to equal 0, and that will let us solve for C1. So it gives us a value of 214 for C1. And we can repeat this process using the position, the deflection equation, because we know deflection at the wall will also be 0. So that's going to let us solve for C2. If we plug in x equals 2.5, then that's the 8.33 2.5 cubed and 0.3 2.5 to the fifth, gives us a value for C2, negative 377 for C2. Now it's possible we could have originally reversed our coordinate system and had x equals 0 at the wall. That probably would have made these C values 0, but I didn't think about that till just now, and it's too late to change. There's no going back at this point. But at least it'll make this next step a little bit easier. If we're looking for deflection at A, now A is at point 0. So we're just plugging in x equals 0 to find the deflection at point A. So it made finding C a little bit harder, but it now makes the deflection at A a little bit easier. And now I am remembering to include EI, right? It used to be EIV on one side, so I have to divide EI over to the right-hand side. So all of this 0 to the fifth and 0 cubed and C1 and C2, all of this gets divided by EI to give deflection. So I gotta scroll back up because I forgot the numbers, 200 gigapascals for E and 0.000129 for I, the area moment of inertia. So solving for beam deflection. In order to make sure we get units of V in regular meters, we need to make sure, double check that all the units are in regular normal units. So Young's modulus E in Pascal, area moment of inertia I in meters to the fourth. And I get 0.000146. And of course, it still looks like I messed up the units because when I solved this from superposition, it was just 0.0146. So what did I do wrong? I used the exact same values for E and I that I used before. And now I see the issue. I've been in kilonewtons this whole time. The 50 and the 90, these were kilonewtons. When I did superposition, I remembered to do 50,000 and 90,000. But all of my M and V equations, these have all just been in terms of kilonewtons, not newtons. I should have converted those back at the beginning, but since I forgot, I can still do the conversion now. So I just need to multiply by 1,000 to cancel out the kilonewtons to convert it back to newtons. And that's going to give me the 14.0146 meters or 14.6 millimeters. So this does match. I did get the same answer, both methods. Superposition, way better, way faster. Only do double integrals if you find yourself in a situation where you have loading that does not match your superposition tables. Don't forget to hit the thumbs up button, and down in the description you'll see the playlist for my full mechanics and materials playlist. Go ahead and bookmark it for later so that you can come back and watch next time you have a homework question. Good luck on your next test.